All right, today we're going to talk about the order of convergence of a sequence. And when we say that a sequence Pn from n equals 1 to infinity converges to a limit p of order alpha, this means that if we compute the limit as n goes to infinity of the absolute value of Pn plus 1, maybe I'll write that a little nicer, Pn plus 1 minus p over the absolute value of Pn minus p to the alpha power equals some constant lambda. Okay. So just a few things to point out here. This p is the limit of the sequence. Maybe I'll make a note of that. It's the limit of the sequence. Okay. This alpha is what we're calling the order of convergence. And we'll, if alpha equals 1, we say this is alpha equals 1, this is linear convergence, or converges linearly. Oops. Convergence. If alpha equals 2, we say this is quadratic convergence. Okay. And then lambda is a constant. So this is saying if I compute this limit, this relationship between the Pn plus 1 error, really, the difference between Pn plus 1 and the limit p, and the error in the nth term, or Pn minus p, and I raise to the alpha power, and I get a constant here, lambda, then we have this convergence, this order here. Okay, well, let's do this with an example. Let's show that the bisection method, algorithm gives a sequence with error bound that converges linearly to 0. Okay, so we're really thinking about the error bound for the bisection method, and we want to see how quickly this error converges to 0. And we're already told that this converges linearly, which means we're going to use this definition with alpha equals 1. And our limit is 0, so that's this p term that we're going to have in our computation. Now, the error bound for the bisection method looks like b minus a over 2 to the n, because you're dividing the interval in half n times. And so let's say this is our error term. This is the error bound. So this is going to be the term in our sequence, this Pn term that we're thinking about. The limit I actually want to compute, the limit as n goes to infinity, has the n plus first term in the numerator. So I'm going to take this expression, and I want this to be in the n plus first term. So b minus a over 2 to the n plus 1 minus the limit, which is 0, absolute value, all over the nth term in our sequence. So b minus a over 2 to the n minus the limit term, 0, in the absolute value. Okay, so just to be clear, this term here is playing the role of Pn plus 1, and this term is playing the role of Pn. Okay. Now we're just going to go ahead and compute this limit. So let me move it over here. Okay, so we have the limit as n goes to infinity of, we've got b minus a over 2 to the n plus 1 minus 0, so this is our numerator term, times this fraction is in the denominator and it's minus 0, so I can sort of ignore this part. I'm not really changing anything. So if I think about just this piece, because minus 0 is not going to change it, I have a fraction in the denominator, so I am going to take the reciprocal and multiply. So I have times 2 to the n over absolute value, over b minus a in absolute value. But 2 to the n and 2 to the n plus 1 are both positive numbers. And n is greater than or equal to 1 here. So really I have absolute value of b minus a over 2 to the n plus 1 times 2 to the n over absolute value of b minus a. So now I can cancel out these b minus a terms. So I have the limit as n goes to infinity of 2 to the n over 2 to the n plus 1, that's 2 to the n times 2. So now these two terms cancel, and I'm left with just 1/2. I didn't point this out, but I should say we're computing this limit. Specifically, I should have noted that we have a 1 in the numerator, or sorry, in the exponent here. And that's what I'm calling lambda. I'm sorry, this is what I'm calling alpha. That's the order of the convergence. And because we were told that this sequence converges linearly, I'm computing this the limit of this ratio with a 1 in the exponent here. That's where the alpha is. If we had a sequence and we said, show this converges quadratically, I would put a 2 here, and then I would compute the limit and show that we get a constant. The constant that we end up with, this is this lambda that I mentioned earlier. This is lambda. This is called the asymptotic error constant. Error constant. Okay. So really, you're comparing the error between the sequence, the n plus first term of the sequence, and its limit. So whenever you're subtracting something like this, you think of it as an error because this is where we're converging to, and this is one of the terms. So this is the error in the n plus first term. And we're comparing that to the error in the nth term. And somehow this term is going, it's like comparing the previous error term raised to the alpha power, and that's what's giving us the order of convergence of our sequence. Okay, so this is how you would show something converges linearly. If you were showing something converges quadratically, you'd make this a 2, but you'd compute this similar limit. Again, comparing the Pn plus 1 error and the nth error. So I hope you found this helpful, and let me know if you have any questions.